Now we will speak about finite strain with some practical exercise. Okay, as you know about the deformation, strain is quite heterogeneous. We have observed this heterogeneity in crustal scaly shear zone. For example, the horizontal shear zone has a deformation concentrated in a high strain shear zone to the north in Variscan Belt in Sardinia. To the south, the deformation is characterized by folds. So usually deformation at the natural scale is heterogeneous, but it is always possible to find a small volume of rock where deformation could be regarded as homogeneous. That means that every point in this small volume has been characterized by exactly the same amount of strain. So even in a fold, we are in a fold, more or less, you can find a small piece of the fold in the limb or in the hinge where the formation could be regarded as homogeneous. In this way, we can apply finite strain. We can try to quantify the amount of deformation suffered by the rocks. As you know, deformation could be continuous or discontinuous. Discontinuous deformation give rise to fault, break, discontinuity in the rock mass, whereas continuous deformation is very interesting because in this case we can apply our methods of finite strain. So small homogeneous volume and continuous deformation with no break. Okay, just we recall some basic feature of deformation. Uh, you know that we can have a change in length of line. We observed Boudin. Here is a nice example of Boudin in Greece by Paris Xipolias. Some more competent layers has been broken into pieces, and each pieces is standard with respect to the other. In a situation like this, we can take a quantitative measurement of strain by summing up the length of these bodies, L1, L2, L3, L4. So we sum up and we have the initial length of the line before stretching. And from this point to the other one, including the Boudin and the space between one Boudin and the other, we have the final length of this line. So we can calculate extension by il L final L minus initial length divided initial length. In this way, we can calculate the extension suffered by this line. If we are in the case of extension, E is positive. If we are in contraction, in shortening, you are measuring the deformation along a fold, E is below zero, is negative, because you have contraction. The final length is less than the initial length. This is a case of folds, also from Greece. You have folds like this, then you can uh, measure the length of this red line, so this initial line, and this is the final length. The final length is less than the initial one, so your calculation give a negative extension, contraction. There are other ways to represent linear deformation. It is lambda is 1 plus e elevated this exponent, and also the stretching is 1 plus e, just different way to represent elongation of lines. As you know, there is also the shear strain that is just the tangent of the angle in between this straight line and the distorted line by simple shear. This angle, the tangent is just the amount of simple shear that is related to amount of displacement during deformation. So in the last days, this kind of deformation. As a change in angles, there are some beautiful examples from the Moin Trust zone in Scotland, because this is a trust connected to the Moin Trust. Let me show you the lesson before. Below there are quartzite or pipe rocks of 150 million years. Pipe rocks means that you have this kind of burrows that are distorted by the strain, because we are a strain like this. So these burrows are no longer perpendicular to the backdin, but that has been distorted by simple shear. So you can simply take a measurement of this angle and gain the information about the shear strain just in the field with pipe rocks, with warm burrows happened in the Cambrian and then deformed a little bit after. Of course, also in the shared zone, this is one of the shared zones that I show you from Capo de Creus in northeastern Spain. You have an older foliation deflected into parallelism with a shear zone. You can take an estimation of the shear strain by the deflection of this foliation that progressively became parallel to the shear zone. There's another possibility to apply shear strain. Okay, this just the variation in shear strain at small scale. You can take a measurement of shear strain along a different section, and you can gain different values, because the formation is heterogeneous not only in this direction but also in the direction of shearing, as we saw from the example by Fossa and Cavalcante of the shear zone in the Adamello region. Just it is not in a normal situation, but is normal to find this kind of things. Okay, now we recall a little bit about the strain ellipse. After you have undeformed state represented by a circle, after homogeneous deformation and continuous deformation, this circle became an ellipse with a long axis and a short axis. So the fine strain means to characterize the shape of the ellipse in the deformed state. Of course, changing from a circle to an elliptic shape, this part has been shortened. This part has been lengthened, the red one, to gain this final shape. This is just okay. And when we deal with the deformation, we have obviously all the lines are shortened or elongated, and change the angles with respect to the main axis of the finite strain. Only two axes remain perpendicular, the short axis and the longest axis, Z and X, that are called the principal axis of strain. They are quite important because in 3 dimension they help us to recognize the foliation in the rock and the x epsilon plane in the deformed rocks. So usually in 2 dimension we use the ratio from the length of the longest axis x and the length of the short axis, this one. So this divided by this one. This characterize axial ratio characterizes the shape of a ellipse. Okay, in 2 dimension. Okay, this is no more important. Okay, so when we try to apply this kind our method to deform the rocks. Here we have a good example of a Triassic rocks deformed in the Northern Apennine. We have cluster of marble, of quartzite, and you can see that these clusters are elongated in this direction and shortened in this direction, maybe along the main foliation. Um, and why we use ellipse to take information of the strain? Because many rock element, mineral, cluster, display an elliptical shape after deformation, or a shape very close to an elliptical one. So in this case, they are not true elliptic. You can see a shape like this, very irregular or rectangular, but you can fit an ellipsoidal shape inside this object. So you can approximate this object to an elliptical shape. And of course, you cannot use only one cluster of this deformed breccia, this metabreccia, but we have to use many classes, maybe 40, 50, to have a good indication of strain. Here there is a problem because the class have different composition, um, marble clast and the quartz clast. You can see the marble clast are very strongly flattened and shortened. Quartz clast are remain more or less rectangular or more or less spherical in shape. So there is a big difference in contrast in rheology between this one and this one. So if you use marble cluster, you can have value of strain that is quite different from this one that underrepresent the strain undergone by the rock because it is too strong. Is well deformable, so more or less mark the deformation history and all the strains underwent by the rock. This one is not good. Anyway, just in a theoretical way, if you take information by this kind of cluster, you can estimate the different rheology, different viscosity at the time of deformation. Okay, finite strain is useful for the study of fold kinematics. If you put strain ellipses on the fold hinge limbs, you can detect a different mechanism of deformation. They has been used by to detect deformation mechanism, to detect the origin and significance of a planar anisotropies. So the first study is to detect that the x epsilon plane of the finite strain ellipsoid has been made by finite strain analysis of over 100 of sample. They are useful if you try to build up a balanced cross-section in the innermost part of the genic belt, because in the outer part, where you have a thrust and fold related to thrust, you can simply retrodeform the section by linear deformation. But if there is a strain inside the bedding, you have also to calculate strain and to destrain the bedding before make this kind of retro deformation to have a good value of shortening or representation of the initial situation. So every time you have an internal deformation in your bedding, deformed rocks, deformed conglomerates, deformed breccias, you have to calculate strain and to detract strain from the retro deformation. The finite strain has been used to calculate the deformation and to show the variation of deformation around plutonic rocks, around the granites, to try to understand the way in which they intrude the country rock. They has been used for quantitative analysis of simple shear and pull shear component and the volume changes. Because there is another important thing that I forgot to tell you. Do you remember a square like this, deformed by pure shear, simple shear? You have a situation like this, distortion. Okay, some people is able to quantify this kind of extrusion from this part to this part because we have vorticity in between 0 and 1, simple shear and pure shear. But if you add finite strain of the deformed object, so finite strain plus vorticity, you can estimate the amount of extrusion of this ductile shear zone, of this non-coaxial shear zone. And this work has been done by Rick Lowe in the South Tibetan detachment, or other people, Tsipolias in some uh, deformation in Greece. So adding finite deformation to vorticity, you can estimate the amount of extrusion that the rock underwent during no coaxial deformation. So it's a very important finding. Okay. Okay, in this paper, maybe Low and others, 2002, this has been applied to the South Tibetan detachment. Okay. And also, Matteo Simonetti used this method to calculate the extrusion in the Argentera shear zone, adding vorticity values to finite strain values. Okay, to calculate the strain ellipse, we need good strain markers. What is a strain marker? A strain marker is an object that is present in rock before deformation and has been deformed homogeneously and continuously without breaking, without recrystallization, just changing the shape, shortening and elongating according to the overall strain ellipse working in this rock. So for example, there's metaphilites or metaconglomerates, maybe from Greece, in these kind of rocks. Paris Tripolias was able to calculate strain using a lot of these strain marker because there are no fracture. You can see under the microscope there is no recrystallization, no bulging, no grand boundary migration, no other mechanism, no ondulous extinction. So they just change the shape without fracturing or recrystallizing. So these are good strain marker, and they can use this kind of marker to calculate strain. These are deformed breccias. Also, the class of the breccia are very good strain marker. This axial ratio calculated is 6.72. In this section, the ratio is a little bit much more than 7. But also these objects are very useful. Of course, they are big objects. You cannot use the scene section, just a picture in the field, because in scene section you can see only a fragment of the class, of course. Okay, this is a good deformed rock for strain analysis, but not this, because in this scene section you can see that the quartz has been recrystallized, so the original crystal has been lost, and then you can see uh, mobile grain boundaries like this, ondulous extinction, and so this kind of quartzite is not good calculated strain. So you can do nothing with finite strain, or you can calculate strain. You can try measuring this long axis, short axis, but you have a minimal estimate of strain, and just in a small moment of all the deformation history. So you can do more or less nothing with this data. With this rock, with good strain marker, you can go ahead and calculate the strain. uh, you can, the first years, the strain was calculated by fossils, using fossils, with a trilobite distorted by shortening in this direction, elongation in this direction, shear strain here, because they have a strong symmetry, and so you can also calculate the gamma value. But the problem of the fossils is that they are on the bedding surface, not in other place, in other surfaces. So you cannot take advantage of the 3D dimension. Instead, reduction spot the oxidizes iron and reduced iron make this kind of elliptical shape. They are perfect to calculate strain. They are in the volume of rock, so you can use this to calculate strain. Okay. When you have a good strain marker, you can try to use some of the available methods to calculate strain. If you, for example, you have some oolite in a rock, is before deformation, undeformed state represented by a circle. You have this circular shape of the oolite, perfect. The distance between one center and the other is more or less constant. So this length L is more or less constant from this one and the closest, the nearest neighbor. After deformation, you can observe the change of the shape of the circle that became elliptical, and also this line changes the length. This line is elongated, and the new length is L1. This one is shortened because it's close to the shortening direction, and so on. After, of course, this kind of line rotate also into parallelism with the axis of the finite strain. So what we can see after pure shear or simple shear or mix of the two is the change of the shape of the object from circular to elliptic, a change in the length of line, a change in the angle that this line make with the mm, principal axis of the strain ellipsis, and also there is a change in the position of the centroid of this object, because in this direction they are shortened. So these two objects they shorten their distance like this. In this direction, the objects are elongated like this, and the maximum elongation of the distance is in this direction. The maximum shortening is in this direction. So uh, just looking at this simple picture, you can use a different approach. You can use the different the change in shape from circular to elliptic, the change in length, the change in the angle between the lines, and also the change in the position of the centroid of the strain marker. The last method is the so-called Fry method that uses the position of the centroid to detect the finite strain. The other method are the RFI method, uh, mm, using the axial ratio of one object, long axis, short axis, and orientation of the long axis. It is very useful, this method. And there are also other methods, but a little bit complicated, because if you measure the length of these lines, you can have you take a measurement in the surface. You have a situation like this. It was used by Ramsey several years ago. You can have this, the length of a line in centimeter, and this more or less the angle. So more or less you have a sinusoidal shape of the line. So the longest line arrive at this point, the shortest line at this point. So if you make a ratio between this point and this one, more or less you can calculate the finite strain. But it is very long because every segment should be measured with a relative angle, so you need a lot of time. But more or less, you can gain information also by the length of the lines. But this method has been overcome by Fry because he used the centroid of the object that are more or less connected to the length of the distance between the different objects in a very easy way, much more easy way. Okay, the strain analysis by RFE method is quite easy, not so easy to do manually because you need to take a lot of information. More or less, we need to estimate the long axis, the short axis, to have the ratio, and the angle between the long axis and a main direction. In this picture, you can see undeformed state with object with the same axial ratio, initial axial ratio equal to 2, and the different orientation of the ellipses 1, 2, 3, 4, 5, 6, 7. If you plot in a graph where you can put here the axial ratio and the orientation from 0 to 90, from 0 to minus 90, you start from this position because all these objects have an axial ratio equal to 2, so you have to project all the ellipses in this line, okay, undeformed state. If you start to deform it by homogeneous deformation, you have contraction here, extension here. What you observe is the change of the shape of this elliptical object. They rotate a little bit, and their distribution, when you take measurement of long axis, short axis orientation, the distribution is no longer along a line, but they go in a curve like this. Because, for example, if I take this object is vertical, but vertical is also the shortening. So this object became shortened, and when you reach a deformation similar to 2, it became spherical. Okay? So this is the minor axial ratio that you can measure on the graph. The opposite happened to this kind of class because it is oriented parallel to the long axis, so this is shortened, elongated much more. So again, the much higher axial ratio here, the number 7, the number 1 is here. All the other objects are in this position between the highest and the minor, the less deformed object in this distribution. If the strain, axial ratio of the strain is 1.2, that is minor than initial axial ratio of the object, the distribution is from 90 to minus 90. All of the orientation are more or less preserved. If you increase the strain, and the strain ellipse has axial ratio equal to 3, 3 is more than 2, of course, this reasoning go ahead. This object became spherical, and after that became flattened in this direction, elongated in this direction. But it is a less deformed object in the group, and it is in this position. The ellipse 7 continue to be stretched in this direction and short in this one. So the axial ratio is the maximum and is this point in this situation. And the other are in a closed shape, in a curve with a closed shape like this. So more or less, when you project your data on RF phi angle, phi is the angle that I measure here. If you have a dispersion from 90 to minus 90, means that the deformation is less than the initial axial ratio. When the point are distributed in this way in a closed curve, means that the strain is higher than the initial axial ratio. Okay. This is an example by Tripolias, just on the on this kind of deformed quartzite. So they used this class as a strain marker. I projected on the RF graph, just rotated in this way. You can see that, of course, the cluster not along one line, but occupy different line because you have different initial acceleration. It is not equal to 2 as in the case before, but you have a different initial acceleration, so they occupy a closed area like this. Okay. Okay, this method was developed by Ramsey, then was used also by Dannett in the 80s. Then Lyle, Richard Lyle, applied also different object, different lines, because these are lines of initial uh, axial ratio, of the same axial ratio. This one, there are other one, and also he used the theta lines that are the loci of the objects that have the same orientation. So other line in this way, uh, over each line there is an object with the same initial orientation. So he made an improvement in this method because at the beginning people use it manually and they try to fit the point above the line that has been constructed by former computer. So it was a manual fit and it was not easy. But with the theta line, it was much more easy to fit and to try to find the final result. Okay, I assume that more or less you know this method. Uh, there are also variation using tensor calculation because you can put the axial ratio and the orientation in a two-dimensional matrix of deformation. There was a method by Shimamoto and Ikeda, I don't remember 19 something. It was a numerical method. And more or less, if you use the arithmetic mean of the RF and the arithmetic mean of the orientation, you can have just an estimate of the finite strain. Okay. Otherwise, you can use some pre-prepared graph by Lyle. There is a book with different graph constructed by for different RF and different strain applied. You have to project your data and to put above this graph to try to find the best fit. Okay. So it is very time-consuming method because you need to have at least 50 objects in a section. 50 objects means 150 measurement of axis and orientation. Then you project on a tracing paper for one section, then you put above the pre-constituted graph and try to find the best fit just for one section, but you need in three dimension at least two sections, so you need to make 300 and more measurements. It's very time consuming. But now with the software developed by Volmer, it is much more easy because you can just try to obtain the data of the axis and the centroid orientation, and then they apply the method for frame method, RC, and so on. Okay. And of course, if you use this method of finite strain, it is based on the changing in shape of this object, but you are not sure that this object is deforming in the same way as a matrix. Should be a difference in competence contrast. Mm. Competence contrast is visible because maybe the foliation is wrapped around this cluster. So maybe this method underestimates the real strain a little bit. Mm. So, for example, Norman Fry, an English geologist, uh, uses this kind of change of the lines in between the packed fully packed object of around maybe lights, because in the formed state these lines are more or less of the same length. After deformation, these lines are deformed according to the strain ellipse. So you can take a single measurement of this line, this line, this line, and project in a graph like this, like the one I put there, or he developed a simple method, a graphical method that is quite easy, because you have to take a picture. You have a tracing paper. You put the center of tracing paper here. You put the tracing paper above this, or better, you can put above and mark the position of the center like this. Ta, 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 ta. Then you can take a second tracing paper, this one, two. You put above this your center, the center two, you put on this position, and you mark the position of the center around. You shift to this point and mark the position of the point around, and so on. Maybe it is better to to put number to avoid to repeat the same thing on the same point. And after at least 50 displacement of the tracing paper, you have to take care not to rotate the tracing paper. You have to translate parallel to the axis with no rotation. If you do this after 50 displacement, you can show a distribution of a point with a high density cloud here with low density point in the central part. This is just the strain ellipsoid. It's proportional to the strain ellipsoid. So if you take the long axis and the short axis, make the axial ratio is the axial ratio of the strain ellipsoid. It is the same as go to take consideration this one, this one, this one, and make a long calculation is exactly the same, because the principle is the same, but he was able to find this very quick method, because if you have in section or a picture, you can apply in a few minutes, maybe half an hour, listening music, maybe so. Because not it is not so difficult, no? Just to repeat the point, you can watch television, maybe. So it was very popular, this method, and moreover, it it will take in consideration the position of the cluster, but not the shape. So you can have also a strong difference in contrast, in competence contrast between the matrix and the object, but the object changes the position in the space, so you record the strain in a good way. Okay, be careful, because prime method can be used. Okay, also on rocks that have a pressure solution along grain boundaries. If the grain is not dissolved completely, you can use at the same time, but you take care. Okay, and usually is applied to sand grain in sandstone, voids in limestone, pivots in conglomerate, but you can use also in feldspar, maybe deformed rocks, but usually is applied in this condition. Okay, of course, using the Volmer program, you maybe you can mm, utilize the perimeter of the object and calculate the major axis, minor axis, and the position of the center. Then the output could be RP method, Fry method, without do much more calculation. Okay, but what we need is to calculate the strain in 3 dimension. So the best way is to use the principal plane of the finite strain ellipsoid. A strain ellipsoid is made by long axis, intermediate axis, and shorter axis, A1, A2, A3, or X, epsilon, Z. But if you use two of these plane, you are able to calculate strain. If to use other section, you must calculate strain in a very different, very complex way, because you have to do a long calculation to gain information of the principal plane. So the best thing is to use the principal plane of the finite strain ellipsoid. Maybe the xz and the x epsilon, that is the foliation of the rock, is the lineation. So when you go in the field and you take your oriented sample, so you are in the field, you have a lot of rock, you have a foliation like this in the rock, you you mark the orientation, the, the strike of this surface, marking the direction of the north, the dipping, maybe north 120, 55 degrees toward the southwest. This is orientation, and you mark on the sample. Then you broke the sample with the hammer. Usually it breaks just when you put the orientation. You took away the sample, then you go in the laboratory, and you will try, of course, to break the sample along the foliation, because it is a very easy plane to break rocks. And if you have the foliation like this, maybe you have conglomerates. So the foliation is this plane of the strain ellipsoid, one of the principal plane. On this plane, you can observe the elongation of the object or the growth of mineral in a preferred orientation. So this is the maximum axis of the strain. So you need to cut this rock in 2 sections, at least 2 sections. One should be the foliation, if it is enough good. The other one is perpendicular to the foliation and parallel to the lineation, where you can see the maximum deformation is a xz plane. So with two plane, you are able to calculate the third one. So you characterize completely the finite strain ellipsoid. Otherwise, if the foliation is not good, you can cut the sample uh, not parallel to the lineation, but perpendicular to the lineation in this way. And you have the third section of the finite strain ellipsoid, that usually show less deformation because you have a maximum shortening and intermediate axis. The maximum deformation is visible on this section, XZ. Maximum elongation, maximum shortening, so maximum deformation. Because if you have, for example, the axial ratio on this plane and the axial ratio on this plane, you need to calculate the axial ratio on this plane. So you just divide this axial ratio by this one, and you obtain Okay, is opposite. No, you have this one, sorry, XZ. Okay, okay, this is exception. So you divide these two ratio and obtain the epsilon z acceleration, just to have the deformation of the three plane main surface of the finite strain ellipsoid. Just it is quite simple. Okay, so when you have a deformed sample, you must cut along two of the three main principal plane of a strain ellipsoid. Because if you have a cut oblique to the to the principal plane, maybe you you cut in this direction, you have a component, and then you need at least three different cut or more, and you need to calculate by matrix deformation the principal strain, but it is quite complex. There is a paper by Owens at the end of the 80s with all the calculation. During the PhD, I tried to write a program to calculate this one. It was very complex because you need at least three or four surfaces. You have a much more surfaces better. So a lot of work, especially at that time that I worked manually. So several months of work. So the best thing is to have one of these, two of these three principal planes. Then the work is much more easy. Okay. Okay, this is a sample from Sardinia. There are Cambrian breccias uh, formed along a fault escarpment during the extension of the Cambrian continent, the southern Cambrian continent. And this breccia, carbonatic breccia made of limestone, more or less, are deformed, are strongly deformed. And I took a sample. The sample is cut along the XZ section, where you can see a strong elongation and a strong shortening perpendicular is a good section. The other one is a perpendicular section, and you can see that there is a small elongation, not so strong like this. So you can also infer the kind of ellipsoid, because if you had elongation in this surface, you are more or less z epsilon elongate x elongate, so you are in pancake ellipsoid more or less. If in this section you observe circular object, probably you are in a Sega shape ellipsoid. So you can have just qualitative estimation of the strain ellipsoid. Okay. So usually, if you give a look to this section, you can more or less assess if you are in general constriction or in general flattening or axial flattening. So of course, you have to calculate exactly the acceleration to project on the Flynn graph, but you can have an idea of this one. So in this kind of object, prolate result, in a section like this, you can observe circular shape. Mm. In this one, you can observe elongated shape everywhere because it is like a pizza. You cut a pizza in every direction, and you can see everywhere the elongation of the object. Okay, when you use finite strain, usually you project your data on the Flynn graph, so you can find the coordinate of the point here, and you can assess the kind of ellipsoid. But keep in mind that this line is where k is 1 is for mm, condition of deformation with no change in volume. If the volume decrease, this line shift to the right. If the volume increase, this line shift to the upper part. But if the volume is in between, the less of the gain volume is in between minus 20 or plus 20%, more or less, this line is a good approximation. So you have to check also to have not so much loss or gain of volume in the rock. Okay. Of course, the kind of deformation, the kind of strain ellipsoid uh, make different kind of rock because in this part, in the pizza shape or pancake ellipsoid, you have mainly a foliation but not a lineation. You cannot find delineation here because a pizza is round and every direction is the same. So you cannot assess the occurrence of of elongation lineation above. So this is S tectonite. S means schistosity, foliation. This you can start to have a lineation on the foliation. In this field, there is a better situation. You have a good foliation, a very good lineation, so you can um, verify very well the principal plane of the strain. Here you can have less foliation and much more developed delineation up to cigar shape ellipsoid where you have only lineation and no foliation. So in the field you sometimes it is difficult to find the foliation or to find the lineation because you should be magari in this position or in this other condition. So it depends also on the kind of deformation. Okay, just an example. Okay, we can go ahead. In this picture, it is represented more or less the field of flattening. You can see more or less little bit stretching lineation here, but not so strong. And XZ and epsilon Z section are more or less similar, not much difference. You have much more difference in the plane strain, so there is a good delineation. Is much more strong deformation, less deformation. In this part, you have a stretching lineation, strong deformation here, and no deformation in this phase. Okay, no problem. Oh, this is just an information. You can see the filling graph and this kind of strange plot. Do you know what are they? Oh, you can see here indirect evaluation of 3D strain by quartz C fabric. Okay, there are methods to take measurement of quartz C fabric, quartz C axis under the microscope. You can use a universal stage. You can take a crystal of quartz, so you rotate until the C axis is vertical, so it completely in extinction. And to do this, you need maybe 4 or 5 days for one scene section because you need 500 of C-axis, and then you project all the observed C-axis on a stereographic projection, and they try to build up this kind of skeleton. That is the distribution of C-axis is not uniform, but just follow this geometry that is controlled by the shape of the finite strain. So if you have a distribution of C-axis like this, you are in plane strain. If you have a distribution of this like this, you are in apparent flattening, or this apparent constriction. And this is for the C-axis of the quartz, the main axis. This is for the basal prism, another axis. This is also important because by measuring the axis, you can also have an estimation of the vorticity of the flow. So, but to do this manually is very long. It is better to put this in section under electronic microscope with electron backscattered machine that collect in few hours all the information about the z-axis, the magnitude of the grain size, so complete information. It is quite expensive, but it's very useful. Anyway, uh, using the z-axis, of course, we have also an idea, an estimation of the 3D strain. It is an independent method. Okay, Cipolias worked a lot on this. These are some graph of the quartz z-axis. Of course, you have contouring, you have maybe 400, 500 measurements, so you have to do some statistic of this graph. And by the position of the maxima, you can try to draw this kind um, of a skeleton. For example, this one is related to related ellipsoid, this one to pancake ellipsoid, this one more or less to plane strain, but you can see that here there is a symmetry of this axis and this one. Here the symmetry is lost, there is a rotation, and it is due to simple shear. So by using the z-axis, you can also assess the sense of shear in the rock. It is very useful. Uh, U means universal stage. It means that he spent several weeks measuring a single axis because when you have scene section, you have to move along three different angles to make the angle. So for every z-axis, we have three angles to detect and to plot. So it's very long. With a automatic machine electronic microscope, it's very very easy. Okay, but just take in mind that it is very useful because you can detect the sense of shear, the vorticity, the kind of strain ellipsoid, and you can use, of course, quartz because it's easy, it is very common, but we use the calcite for the South Tibetan detachment because in central Nepal and western Nepal, the grit element sequence is made by calc silicate rocks in the upper part, and the Tethyan sequence is made by marbles in the lower part. So you have calc silicate and marble in contact. It is very difficult to put the boundary. And so we calculate temperature, by pitting condition, pressure, and also with a PhD by Laura Nania, that she is now working in Geological Survey of Canada. She made a very beautiful work with calcite because calcite is quite difficult as a mineral. It's not simple as quartz, and there are not many people working on this. So she spent several months in Germany with Bernard Leys and Michael Stipe to understand the deformation. But at the end, she was able to publish three papers: structural geology, tectonophysics, and Geological Society of London. The tutor was Chiara Montomoli, and it was very nice work because she gained a lot of information by this kind of fabric. So keep in mind, if you have marbles, you can use also calcite. Okay, now I will show you an example by Xipolias. This is we are in Mediterranean area, Crete Island. This is Greece. Turkey is here. Africa is here. Italy is a little bit on the northwest. He used an app, this red one, with maybe low-grade metamorphic condition, very low metamorphic condition, to assess the strain approaching thrust. Through this PQ unit, it is a local name, but it is not important. So he took sample in a transect, of course, on the surface from one thrust to another. This one, this one, this one. He took several transects. a lot of work for this. And the paper has been published in 2007 in Journal of Structural Geology. It's available. It is a very nice paper to see an application because he found a useful strain marker such as this one. So he used all these kind of elongated quartz grain and the metaconglomerate to assess the amount of strain. So, for example, he compared also, uh, we are on the XZ section by RFE method and by Frey method. If there is a difference in competence contrast, of course, there is a difference in the value by one method and by the other. If more or less a line along a line, it means that they give the same information, so there is not a big competence contrast. So it's just a good check for the method used. Used both the method. Okay. Use a different method, the Frey method, distance of the object, mean object ellipse using elliptical object, mean radial length use elliptical object, a theta curve class to the RFE method use elliptical object. So different mm, different method related to the changing in shape. But they so Frey and RFE is theta curve by Richard Lyle. This is a raffination of the RFE method. So more or less the same value. So all the methods are in keeping. They give good information. This is a good approach because by one single method you have some problem, but using this one different one, you can go much confident of the method. They used also the error bar error on the measurement. It's quite uncommon because usually one put the value, but it's difficult to assess. So more or less, he plotted the strain data with respect to the basal thrust. You have the strain ratio and the distance from the basal thrust. So there is a change in the strain ratio with different values. So approaching the basal thrust, of course, the strain increase up to very high value, maybe 10, 15, a very high value, that very uncommon. Use several different section. Okay, more or less, he checked the same with different approach, but more or less approaching the thrust, the strain increases a lot from axial ratio on the X section close to 3 or less to 3 up to 9, 10, 10, 9, 10. So very, very strong deformation. Okay, you also calculated some other different parameter, but I don't remember what is beta value, more or less. Okay, and at the end, he made also a comparison, a general comparison of the strain value in different situation all over the world. We are the more clean up in the external part of the Alps, Blue Ridge in USA, North Mountain Trust maybe also in USA, Himalayan Trust in eastern Nepal, and the Orleans Trust. I don't remember where is Orleans Trust. D. Cashman, maybe also North America. So you can see that more or less at the distance of few kilometers, and approaching the different thrust, the strain along the section increasing a lot. So more or less the same behavior. This, there is also other part where strain decreases, going away. There are very few value. This is a paper by Goscombe 2006, but maybe after that some other values has been gained. So finite strain is also useful to characterize the amount of strain approaching the thrust, as one of you showed me yesterday, more or less. The most important thing is to have good strain marker and to cut the rock along the principal plane of the strain ellipsoid. Okay, now I show you a little bit something about the software strain ellipse fit by Frederick Vollmer. This the reference, the web page, but you put ellipse fit on Google, you find quickly. It is a very nice software. There are several versions. Just a few months ago, 3.7, 3.8, 3.81, 82. We continuously improve the software. I prefer the older one because they are very simple. Because in the new one, it put a lot of statistics. Of course, it's very useful, but the manual is very complex to read. Anyway, uh, you can use some picture. This is a picture for a conglomerate that is present in the web page. You can use or the picture or the tracing paper with the boundary of the object. Automatically, it is very difficult to gain the shape of the object because you can use Photoshop, for example, or ImageJ, but you have to work a lot manually because the rock are strain are very complex, and if you have a picture like this, it is not easy from a picture to select contrast, binary image, and to select correctly the boundaries. I usually make a lot of confusion, so you have to work a lot this. So one possibility is to use a tracing paper. So use a tracing paper. Manually, you draw the boundaries, and then you make a picture and work on. Otherwise, you work on directly on the picture, and you can you can gain the information about the boundary and the axial ratio in different way. These are deformed object. There is a function that you put the mouse here and you fill of a yellow the object and then calculate the volume, the area. But if the object is open or there are some pixel with the same color outside, maybe the yellow go boom all around the section. Otherwise, you can check the center point by the mouse and then he records the coordinate. Another possibility is maybe the best one is to find 5 points along the perimeter of the object, just five objects. He detect the elliptical shape, long axis, short axis, centroid, and orientation of the long axis. This is quite quick because just 5 objects maybe take care of to put the more distance point or the shorter distance another one. So you can see the elliptical shape. But anyway, he put the elliptical shape just when you made the last click on the fifth object. So in this way, you gain all the information in a very easy way. After that, he plot the information using a R-phi graph like this. So, and they calculate automatically the R axial ratio of the strain, and they put also on the Frey graph. Okay. Of course, there are other kind of information. Maybe instead of the Flink graph, use this kind of strange graph, but it is not usable. Or this that was used by Wellman, you calculating a strain by distorted angles in fossils. So there are possibilities, but I think Herfy and Fry are the most popular, most useful method. Just two example of the formed object. We are in Sardinia, in the NAP zone, in the central part, in between the forest and the hinterland, and there are volcanic breccias deformed during the Carboniferous, and you can see that the cluster are strongly deformed and aligned in the same direction. So the strain is very high, and what we can say is that the strain is higher than the axial ratio, initial axial ratio of the object, because they are all aligned in the same direction. So when you put in a RFI graph like this, you can find all the point in this position. Mm. But these kind of cluster are very good strain marker. Here's another kind of breccia from the Permian of the Northern Apennines. The breccia reworked as a Paleozoic basement and was later involved in alpine orogenesis, contemporaneous more or less to uh, the Alpi. Apennine orogenesis and alpine orogenesis. You can see different cluster, but different elongation because there are different cluster with different areology, different composition. So in this kind of deformation, it is better to use Frey method because you use only the centroid position because this cluster are much more deformed. This one enriched in quartz are less deformed. So if you use the shape of the class, you make a mix. So the result is not good. But if you use the Frey method, is it's okay. You can gain a good information. Okay, now we can stop maybe 10 minutes, and then we can download the software on your laptop, and then we try